Section 4.3, Babylonian number system. In this section, we're going to talk about the way that the ancient Babylonians used to write their numbers. The Hindu-Arabic number system, which is the system that we use right now, has a base 10 number system. We will talk in a minute a little bit more about what that means exactly. The ancient Babylonians used what we call a base 60 number system. And we will discuss what that means also. So what we mean by base 10, base 60, and so on, we mean that when we move over to the next place value, we are moving over and they represent powers of 10 or powers of 60 or powers of whatever the base is. So the way that we write numbers, the Hindu-Arabic number system, when we move over, we have, for example, the tens place, which is 10 to the first power. We have the hundreds place, which is 10 to the second power. We have the thousands place, which is 10 to the third power. That's what we mean when we say base 10. But the way the Babylonians did it, when they moved over, what they meant was powers of 60, which is sort of strange to us, right? Like 60 to the first power, 60 to the second power, 60 to the third power, and so on. So what we're talking about is the city of Babylon. When we say the Babylonians, we're talking about a long, long time ago, thousands of years ago. It's mostly what's now Iraq, but are also parts of Kuwait, Syria, and Iran. That's sort of the area that we're talking about when we're talking about the Babylonians, the ancient Babylonians. Let me go ahead and share my screen here and we'll talk a little bit more about what we mean by the different bases. So the Hindu-Arabic number system, the one that we use currently, is called a base 10 number system. The base 10 number system is one in which each position has a value that's a power of 10. Consider the number 3,724. Okay, what do we mean by that number exactly? Well, of course, the 3 is in the thousands place, and 1,000 is 10 to the third power, 10 times 10 times 10. The 7 right here tells us how many hundreds we have, and 100 happens to be 10 to the second power, 10 times 10. The 2 right here tells us how many tens we have, and 10, of course, is 10 to the first power. So those are all powers of 10. That's what we mean by base 10 number system. This one's a little strange on the far right. We all know that the 4 in this number is in the ones place. And a lot of people would say, well, that's not a power of 10. It actually is a power of 10. 10 to the 0 power is equal to 1, which is a little strange. We'll talk a little more about that in a minute. But anything to the 0 power, turns out, is equal to 1. So 10 to the 0 is equal to 1. In fact, any number to the power of 0 is equal to 1, with the exception of 0 to the 0, which is considered undefined. So looking at it again, when we look at the number 3,724 in, the Hindu-Arabic number system, the one that we're used to, the 3 tells us how many 10 to the thirds we have. The 7 tells us how many sets of 10 to the second power we have. The 2 tells us how many sets of 10 to the first power we have. And then the 4 over here tells us how many sets of 10 to the 0 power we have. Remember, 10 to the 0 is the same as 1. 10 to the first power is the same as 10. 10 to the second power is the same as 100, and 10 to the third power is the same as 1,000. So this is 3,000 plus 700 plus 20 plus 4. Okay, 3,000 plus 700 plus 20 plus 4 makes this number that we call 3,724. That's what we mean when we say that the Hindu-Arabic number system is a base 10 number system. The ancient Babylonians used what we call a base 60 number system. So their far right place value was they didn't consider it the 10 to the 0 power place value. They considered it the 60 to the 0 power place value, which is still equal to 1 though. Remember, anything to the power of 0 is equal to 1, with the exception of 0 to the power of 0. When they moved over to the next place value, we consider the next place value over the tens place because 10 to the first power is 10. The Babylonians considered it the 60s place because 60 to the first power is 60. And when they moved over again, it wasn't the 10 to the squareds place. This is not the hundreds place for the Babylonians. It was the 60 to the second power place. It was the 60 times 60, which is 3,600. This place value right here didn't say how many hundreds there were in the number. It says how many 3,600s there were in the number. And when they moved over again, instead of this being the thousands place, like 10 to the third, it was actually 60 to the third, okay, which is 216,000. We actually still have some base 60 in our life right now, the way we tell time. When we hit 60 seconds, we go to the next thing, we call it a minute. When we hit 60 minutes, we go to the next thing, we call it an hour. So we actually, that comes from the Babylonians, right? So we actually, thousands of years later, still use base 60 a little bit in our lives. The Babylonian number system that we're going to start talking about today actually started around 3000 BC, which is 5,000 years ago. It's a long time, but it wasn't like fully in use in an actual full-on number system until around 1700 BC, which is still almost 4,000 years ago. Eventually, though, like pretty much all other number systems, it eventually got replaced by the Hindu-Arabic number system, the one that we use today. In the Babylonian number system, there are two main symbols. They have a symbol that looks like this, which is equal to 1, what we consider 1. They have a symbol that looks like this, which is equal to what we consider 10. Those are the two main symbols. They do have another symbol, which I'll show you in a minute, that they considered 0. We would consider 0. But these are the two main symbols that make up most Babylonian numbers right here. So, for example, this right here is the Babylonian number equal to 32. It has 3 sets of 10 and 2 sets of 1. So this right here would be considered 32. We would consider it 32. That's equivalent to what we would call 32. This is equivalent to what we would call 2, right? Because there's just 2 sets of 1. So 32, 2. When you look at it like that, at least for these first two examples, it's sort of like the Roman numeral system, right? It kind of should remind you a lot of the Roman numeral system. I know the symbols are a little bit different, but it's sort of the same idea. But it's not exactly the same. And remember, this is the Roman numeral system did not have a it wasn't dependent on a certain base, and we are here. And so we have bases in the Babylonian number system, and we have place values and So it gets a little weird because once you hit 60, you have to move over to the next place value. And let me show you how the Babylonians would move over to the next place value. The Babylonians would move over to the next place value by leaving a space in between. And that's strange to us. That's not how we do our numbers, right? We don't leave a space in between to show that we're moving from one place value to the next. When we write, 3,724, we know that we're moving from one place value to the next because we just write a different digit, right? We write a different character, and that now we know we're moving on to the next place value. But that's not how the Babylonians did it, okay? Since there's no spaces here, for example, this is all in the ones place. This is like 32 sets of one, basically. And since there's no spaces between the numbers here, this is all in the ones place. It's like we have two sets of one. But notice, as soon as I do this, see that space right there? I mean, these two numbers look very similar, but there's no space in between, and here there is a space in between. So this is equal to 2. Turns out this is equal to 61. Why is this equal to 61? Because when we have the space in between, it means we move from the ones place to the next place value over, which is the 60s place, as far as the Babylonians are concerned. Remember, when we move to the next place value over after the ones place, moving to the left, we call that the tens place. But the Babylonians called that the 60s place. And so when you see this space value, this right here means one set of one. Then space value means there's space here means move over to the next place value, and this means one set of 60. So this is one set of 60 plus one set of one. That's why this number is equal to 61, while this number is equal to 2. I know that's strange. Let's look at another example. Okay. Here's a Babylonian number. This whole line right here is one number. This happens to be equal to what we would call 5,485. Let's talk about why. On the far right over there, you see 25, right? Remember, these are tens and these are ones. So 2 sets of 10 and 5 sets of 1. So this is 25. There's no spaces in between those things, and so that means this is all in the ones place. The way the Babylonians wrote their numbers, this is all in the ones place. This means we have 25 sets of 1. But then you see a space here, right? So that means now we're moving on to the next place value, sort of like how we would move on to the tens place in our number system. They don't call it the tens place, they call it the 60s place. So this is 31 sets of 60, right? See the 3 tens and the 1? This is 31 sets of 60. That's what I put right here. And then see the next, there's another space, and they move on to the next place value. This is sort of like what we would call the hundreds place in our number system, because 10 times 10 is 100. They don't call it the hundreds place, they call it the 3600s place, actually. And the 3600 comes from 60 times 60. 60 to the second power is 3600. So this would be our 10 to the second powers place, or our hundreds place. For the Babylonians, this was their 60 to the second powers place, which is 3600s place. So this is saying we have one set of 3600 plus 31 sets of 60, which is 60 to the first power, right? Plus 25 sets of 1. Remember, 1 is 60 to the 0 power. And if you go through the math on all that, it turns out to be 5,485. Okay. Again, remember on the far right, that is the ones place for the Babylonians, 60 to the 0. And move over to the next place, that's the 60s place. right? 60 to the first power. They move over again. That's the 3600s place, 60 squared. If we had done it again, that would be the 216,000s place, which is 60 to the third power. And it keeps going, of course. 60 to the fourth, 60 to the fifth, if we had a real big number. For quite a while, almost 3,000 years, the Babylonians had no way to indicate that there was supposed to be nothing in a particular place. They had no symbol for zero, except they would just use like an extra big space. Like, for example, if they wanted a zero in a certain place value, they would just make the space between the two things extra big. But that's very confusing, of course. That's not a good way to do math, to do numbers. And so around 300 BC, the Babylonians came up with a symbol for zero. So, like I said, originally, for the first almost 3,000 years, these were the only two symbols. But it became very confusing for the Babylonians to do math and to do their numbers without having a symbol for zero. It took them 2,700 years, which is a little long, but finally they came up with this symbol, which represents zero. So this is like these two triangles on top of each other. That's the Babylonian version of zero. So if we look at a number like this, let's talk about what that's equal to. Well, it's equal to 7,211, but let's talk about why. So on the far right, we have 11, right? This is 10 plus 1. This is 11. And the Babylonians on the far right, that's their ones place, or their 60 to the zeros place, but that's their ones place. This means I have 11 sets of 1. That's what you see right there. See the space right here? Now we're moving on to another place value. This is the 60s place, right? 60 to the first power is 60. But this is the symbol for zero. So this means we have 0 sets of 60. That's what that says right there. Then they see the space again, and now we're moving on to the next place value. This is the 60 squareds place. 60 to the second power is 3,600. This is saying I have 2 sets of 3,600, or 2 sets. So 2 sets of 60 squared plus 0 sets of 60 to the first power plus 11 sets of 60 to the 0 power. Okay, remember this is 60 to the 0. This is 60 to the first. This is 60 to the second power. So if you go ahead and do the math, you go 2 times 3,600 plus 0 times 60 plus 11 times 1. That turns out to be 7,211. I think I want to stop my screen share and we'll start doing some examples on the paper over here. So I hope you kind of understand a little bit more about what I mean when I say base 10, base 60. Um, right, for us in the Hindu Arabic number system, the one that we use, this is considered the ones place, but 1 is 10 to the power of 0. This is considered the tens place, 10 to the first power. This is considered the hundreds place, 10 to the second power. This is considered the thousands place, 10 times 10 times 10. The Babylonians didn't use 10. They used 60. So when the Babylonians did something like this, they weren't thinking of it as 10 to the 0. They were thinking of it as 60 to the 0. But that's still 1, right? That's still the ones place. But this is where it goes different, right? This is called the 60s place. The next place value over told us how many sets of 60 they had. Their next place value over told us how many sets of 60 squared, which is 60 times 60. And then if you keep going, this would be their 60 to the third powers place. I think we saw on the other paper that was 216,000. And that keeps going, 60 to the fourth, 60 to the fifth, and so on. The other thing different though, remember when we move to the next place value, we just simply write another character, right? And we know we're moving to the next place value. That's not what the Babylonians did. They had a bunch of stuff here, possibly, and possibly a bunch of stuff here, a bunch of characters here, a bunch of characters here. They indicated they were moving on to the next place value by simply leaving a big space between. Okay, so that's different. That's not how we did it. Okay? So you got your Hindu Arabic base 10, your Babylonian base 60. Um, I had said that a to the 0 is equal to 1. Or I said that anything to the 0 really is equal to 1. And I know that's a little strange. Let's talk about that. Let's talk about why that's the case, right? Like I said, 10 to the 0 is equal to 1. I said 60 to the 0 is equal to 1. In fact, I said anything to the 0 is equal to 1, except 0 to the 0. We consider that undefined. Okay? But anything else to the 0 is equal to 1. So if I put on my calculator, for example, 0 to the power of 0, I know it's hard to see, but it will say something like error. It says error on top up there. Um, it will say something similar if you do that on your calculator. But if I put 10 to the power of 0, it's going to tell me that the answer is 1. Again, I know that's hard to see on the calculator. If I put 60 to the power of 0, it's going to tell me that the answer is 1. Do it on your own calculator. You're going to see it better. I know you can't see this very well. But anything to the power of 0, except for 0 to the 0, your calculator is going to tell you 1 because it is equal to 1. But let's talk about why. A couple different ways I could show you this. Let's say like 2 to the 0. Why would 2 to the 0 be equal to 1? Well, let me show you some other powers of 2. So when mathematicians were first defining how powers work, like 2 to the 5th power, that means 2 times 2 times 2 times 2 times 2. Go ahead and do that. You'll see it's 32. When you do 2 to the 4th power, that means 2 times 2 times 2 times 2, 16, right? So when mathematicians first defined how powers or exponents work, they just defined it as, you know, you do this that many times and you multiply. And that's what we mean by 2 to the power of 5. You take the base and write it down that many times and you multiply, right? Which is fine. And that's how we get these answers. Okay. So these are all pretty straightforward. Well, even 2 to the first power, I think we'd all be okay with saying it's 2. But when we got to 2 to the 0, mathematicians were like, how do we define that one? Like we defined those other ones, by multiplying 2 by itself that many times, but how do I do 2 to the 0? Look at a pattern right here. You see how when I go up, I'm multiplying by 2? Like, for example, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, 16 times 2 is 32. That's true, but that means when I go the other way, I'm dividing by 2, right? Instead of multiplying by 2 going up, I'm dividing by 2 coming down. So 32 divided by 2 is 16, 16 divided by 2 is 8, 8 divided by 2 is 4, 4 divided by 2 is 2. So when mathematicians got to this, they said, let's just keep going. What if I do 2 divided by 2? Well, you get 1, right? And that's why 2 to the 0 equals 1, but that's why 10 to the 0 equals 1. That's why 60 to the 0 equals 1. You would have a similar pattern. If I was doing tens, I would be multiplying by 10 going up, dividing by 10 coming down. I would still get to 1. If I was doing 60 as my base, I'd be multiplying by 60 going up, dividing by 60 coming down. I'd still get to 1 here all the time. This also is a good pattern to show why when we keep going and we have like negatives here, we get fractions in this case, because if I divide by 2 coming down here, 1 divided by 2 is 1/2. 1/2 divided by 2 is 1/4. And then we get 1/8 after that, and so on. So this sort of pattern recognition here is a good way to show why something to the 0 turns out to be 1, but also a good way to show why when you do negative powers, it turns out to be fraction answers. Okay, let's get into our Babylonian number system example. So just as a reminder, we have three symbols that make up all of the Babylonian numbers. We have a symbol for 1, a symbol for 10, and then we have another symbol for 0. Okay. So those are the three symbols that we're going to use in all of our answers when we're doing Babylonian numbers. So in the beginning here, it says, write each Babylonian number as a Hindu Arabic number. Write each Babylonian number as a Hindu Arabic number. This first example is very easy. This is just equal to the number 3. Why is this equal to the number 3? Well, because I got 3 of those. That's it. And there's no spaces. There's no big spaces in between. That's it. Okay. Sort of like the way the Romans would write the number 3. For the next example, this is equal to 21. It's equal to what we would call 21. Right? The number that we would consider as 21, the ancient Babylonians, several thousand years ago, would have written it like that. Why? Well, because it's 2 of those and 1 of those. 21. 2 sets of 10 and 1 set of 1. Sort of like the Romans would do XXI. Similar idea, right? And it continues being similar. I'm not saying this exactly like the Romans because it's not, but part of it is similar idea as the Romans. So this last one, notice there's no spaces. There's no big spaces in between. So this is all still in the ones place, which is weird. Like you might think of this as like a really long number. It's everything here is in the ones place. We're in the ones place until we leave a big space and move over to the next place value. In fact, anything less than 60 for the Babylonians would all be written in the ones place, which is crazy to us because we only basically write 0 through 9 in the ones place. And then it needs to move over to the next place value once we hit 10. But the Babylonians don't need to move over to the next place value until it hits 60. So this is actually equal to 47. 4 sets of 10, 7 sets of 1. Right? We got 4 of those and 7 of those, 47. So the way the Babylonians wrote their numbers, all the way up to 59, it was all basically how many 10s and how many 1s do you have? But once they hit 60, now they have to move over to another place value. Now it gets a little more difficult, a little strange. So let's go ahead and see that in our next few examples here. Okay, so this is a Babylonian number, but it is not all in the ones place because there's a big space here, right? Since there's a big space here, that means this is the ones place and this is the 60s place. Remember how we talked about on the very first page, the Babylonians on the far right was the ones place. Then they move over to the 60s place. Then they move over to the 3600s and then the 16,000s because they're going up by powers of 60. Okay? But the way they told you they were moving over is they left a big space. So what this means is this number is telling us that I have 1 set of 1 and 2 sets of 60. That's what this is saying. Okay. This is my 60 to the zeros place, my ones place. This is my 60 to the first powers place, or my 60s place. It's telling me I have two sets of that plus one set of that. Okay, if you want to think of it like two sets of 60. One set of one. Go ahead and do the math on that. That's 120 plus one. So that number is 121. It's equal to what we would call 121. Two of those plus one of those. Next example. The big space, that means we moved over from the ones place over to the 60s place. Okay. So on the far right is always your ones place, or the Babylonians would think of it as their 60 to the zeros place. Big space means we're moving over to the 60s place because that's 60 to the first power. We would call that the tens place in our place value system, but that's because we're a base 10 number system. The Babylonians were not. They were a base 60 number system. Okay. So what this means is I have this many sets of 1 and I have this many sets of 60. Okay. But remember, these are 10s and those are 1s, right? And so this means I have 11 sets of 1, then I have 10 sets of 60. Think about that. What would that math look like? Okay. I have 10 sets of 60. Let me write that over here. 10 sets of 60 plus 11 sets of 1. Up here, remember, this is 120 plus 1. That's why we said 121. Okay. Right here, this is 600 plus 11. That's why we're about to say 611. Right? My answer for this is 611. So the way that the Babylonians would write what we would call it 611, they would write it like this. Okay, so this number here is equivalent to 611, just like this number here is equivalent to what we would call 121. These are the next two examples as far as moving from Babylonian number system into Hindu Arabic number system. Okay, so this is one example on the top. This is one number, and then this line is a separate answer. Like these are two separate questions, right? Let me do this. These are two separate questions. So this would be a good time if you are feeling confident to pause the video and try to go figure out what this is equal to as far as we are concerned. And then also the bottom example, what is this number equal to as far as we are concerned? And then you can come back and see how you did. Okay, so for this one, I'm just gonna kind of just tell you the answer and then we'll go over it. So see if you got the right see if you got the right answer. 1,934 is the correct answer here. And then down here is a big number, 90,270. So if you got both of those, then good job, and maybe you can kind of, you know, fast forward to the next page. If you did not get those, you should pay attention right now when we explain. So again, remember this is always the ones place. I have 10, 11, 12, 13, 14. So I say the ones place, but they call it the 60 to the zeros place, but that's equal to 1. Okay. I have 14 of those. This, see the big space? That means we moved on to the 60 to the first powers place, which is equal to 60. This is 32 of those. Okay, so I have 32 sets of that plus 14 sets of that. That's how the Babylonians did their numbers. So really we're thinking of it as 32 sets of 60 plus 14 sets of 1, right? 32 times 60 is 1,920, and then of course 14 times 1, if you add those together, you get 1934. That's how we come up with 1934. For the next example, on the far right, that is always the 60 to the zeros place, which is the ones place. Big space means move over to the 60 to the first powers place, which is the 60s place. Another big space means I'm moving now over to the 60 to the second powers place. 60 times 60 is 3,600. So this is saying I have this many sets of 3,600 plus this many sets of 60 plus this many sets of 1. That's what this number is saying. Okay, so how would we write that? Well, this is 25. This is saying I have 25 sets of 3,600. Plus this is 4, right? This is saying I have 4 sets of 60. Plus this is 30 over here. This is saying I have 30 sets of 1 right there. Okay. You go through the math on that, apparently it adds up to that number. So 25 times 3,600 is 90,000. 4 times 60, 240. 30 times 1 is 30. Go ahead and add those numbers up. You're going to get 90,270. So that's how the ancient Babylonians would write 90,270. They'd write it like that. This big, long thing. Those spaces are very important, right? Spaces are a big deal. So when you're writing these numbers out, make sure you emphasize those spaces. That's how you know, that's how you tell the reader you're moving on to the next place value. For the rest of our time in this section, let's go ahead and switch the order that we're doing this. Let's start with Hindu Arabic and move to Babylonian. The first several examples, we went from Babylonian to Hindu Arabic. Let's reverse that right now. Write the Hindu Arabic number as a Babylonian number. We're going to do several examples like this, but these first 3 examples are actually pretty easy. And the reason they're pretty easy is because they're all less than 60. So that means everything's going to be represented in the ones place. That means I don't have to worry about the space and moving on to the next place value. If you're talking about a number less than 60, it's very straightforward. You just say how many tens and how many ones you have. You don't need to worry about moving over to the next place value. So these are going to be very simple problems here. Right? The way the Babylonians would write 7 is they would simply put 7 of those. That's it. Very simple. That's how the Babylonians would write the number 7. The way the Babylonians would write the number 22 is they would put 2 tens and 2 ones. That's it. Right? They would put 2 of these tens plus 2 of these ones. That's 22. It's very easy if you're talking about a number less than 60. It's very straightforward the way the Babylonians would do it. Even 53, right? They're just going to put 5 of those and 3 of those. That's it, right? And so 5 of those, 3 of these. 5 sets of 10, 3 sets of 1. As long as the number's less than 60, it's pretty easy to do Babylonian numbers. But once you get a number that is 60 or more, it gets a little harder because you have to move on to the next place value and it's going to be a little more difficult. So our last few examples are going to be a little more difficult than these first 3. So the next example is 184. This is definitely bigger than 60. And so we're probably going to have something in the ones place, and we're probably also going to have something in the 60s place. Are we going to need to go into the next place value after that? Let's see. I guess what I might do is I would say, well, let's see. Whatever I put on the far right represents my 60 to the zeros place. Whatever I put in the next is going to be my 60s place. Whatever I put in the next is going to be my 60 times 60s place, which is 3,600. But that number's not that big, right? Number we're dealing with is not that big. So I don't really need to worry about that place value. I'm probably going to have to deal with 2 place values, not 3. But I definitely need to know how many sets of 60 go into 184. How many sets of 60 go into 184? And so what that means is I'm probably going to need to do some long division. For me to tell how many sets of 60 go into 184, I'm going to need to take 184 and divide it by 60. And you can just do long division like you normally do, or you can get your calculator and do 184 divided by 60. When I do 184 divided by 60, you can barely tell here, that's 3 point something. 184 divided by 60 is 3 point something. So just take the 3, ignore the decimal part, just take the 3, and then multiply 3 times 60. 3 times 60 is 180, and then the way we do that is we subtract and we get a 4 right there. So you can use your calculator to help you do the long division. Just use the regular divide sign. 184 divide by 60. You should see that it's 3 point something, but just ignore the decimal part, just write down the whole number part. And then we went 3 times 60 to get that number, and then we subtracted. This is my remainder. So the way it turns out, this 3 actually tells me how many sets of 60 we have, and this 4, the remainder, tells me how many sets of 1 we have. So our answer is going to look like this. We're going to have 3 sets of 60 plus 4 sets of 1. Now, 4 sets of 1, to show that I'm moving from this place value to the other place value, remember we leave a big space there. So make sure you leave a very big space and then put your 4. Because if you didn't leave your space, then people would think you're writing the number 7, right? If you just wrote 3 and then 4 with no space, that's 7. But if you write 3 and 4 with that big space right there, it's actually equal to 184. It's very different, right? So this is my answer. This is what it would look like the way the Babylonians would write 184. 3 of those, 4 of those, right? 3 in the 60s position, remainder goes in the ones position. I mean, we're basically saying 3 times 60 plus 4 times 1, right? That's how you can get that. 3 times 60 plus 4 times 1. So when we're changing from Hindu Arabic to Babylonian, we need to do long division if the number we're dealing with is 60 or more. So let's try 1,202. Maybe this is a good time for you to pause the video and try this on your own. See how you do. I would probably do something similar like I did over here. I would say, well, okay, I know the far right side is my ones place. And then the next one is my 60s place. And the next one is my 60 times 60 or my 3600s place. But that number's not that big. I don't need to go to the 3600s place. There are no sets of 3600 in there. So once you hit a number that's bigger than that, just say, okay, I don't need that, but I do need these two. I should first try to figure out how many sets of 60 go into that. So I should actually take the 1202 and I should divide by 60. Get on your calculator. 1202 divided by 60. What do you get? You should get 20 point something, if you can see that. 20 point something. Okay. Just take the 20, ignore the decimal part, but write down the 20 right there. Okay. And then you're multiplying 20 times 60. Go ahead and do 20 times 60. That should give you 1200. And you are subtracting, and we get a 2 right there. So basically, there's going to be a 20 in my 60s position and then a 2 in my ones position. There's 20 sets of 60 plus an extra 2. And so we're going to put a 20 here. Then we have the big space, and then we're going to have 2 over here, and that's it. That's the way the Babylonians would write 1202. See the 20 right there, and then the remainders go in your ones place. 20 sets of 60 plus 2 sets of 1. If you did that on your calculator, 20 times 60, and then get that answer, and then 2 times 1 and get that answer, and add those up, you would get that. Same thing up here. If you went on your calculator and did 3 sets of 60 plus 4 sets of 1, that would be the same as 184. So long division is necessary when when you're when you have a number 60 or more and you're trying to switch from Hindu Arabic into Babylonian, you're going to need to do long division for sure. All right, next example. 1711. That's a Hindu Arabic number. Let's switch that into the way the Babylonians would write that number. I would probably start by doing what I had shown earlier, 60 to the 60 to the 0 is the ones place, 60 to the first power is the 60s place, 60 to the second power is the 3600s place. But as soon as you hit a number that's bigger than that, that means we don't need that place. That means this is only going to take up 2 place values, not 3. So that means I start by dividing 1711 by 60. I don't need to divide by 3600 because 3600 doesn't fit into there. I start by dividing that by 60. Okay. So go ahead and do 1711 divide by 60. You can use your calculator if you want, okay, unless you just really enjoy long division without a calculator, which is fine. 1711 divided by 60, you should get 28 point something. 28 point something. Just take the 28, ignore the decimal part. Then we go 28 times 60, and we put that answer right there. 28 times 60 is 1680, and then you subtract. And you should get 31 when you subtract. So that and that's your 60s place, that's your ones place. After you divide by 60, whatever you get for your remainder is always going to go in your ones place. I'm basically going to put a 28 in that spot and a 31 in that spot. But we do it the way the Babylonians did, right? So the way the Babylonians wrote 28 was 20 and then 8. 1, 2, 3, 4, 5, 6, 7, 8. That's the way the Babylonians wrote 28. And remember, so that's kind of right there. And then they leave a big space until they put the next one. So they leave a big space, and then the 31 goes over here. 10, 20, 30, 1. That's the Babylonian version of 1711. The 28 goes there, the 31 goes there. 28 sets of 60 plus 31 sets of 1. If you did that, 28 sets of 60 plus 31 sets of 1, parentheses would mean you would multiply those first and then add the answers at the end. You would get 1,711. Next example. 7,384. I'm going to do a similar thing like I did on all of them so far. I say, okay, we got the ones place, 60 to the first, we got the 60s place, 60 to the second, we got the 3600s place. Now, that number is bigger than 3600. So I'm going to actually keep going on this one. 60 times 60 times 60 is 216,000. Now, that number is not that big, right? But it is bigger than that. Okay, so I'm not going to need that place value, but I am going to need this. So I'm going to need to utilize 3 place values in this one. I need to start by dividing 7,384 by 3,600. So the long division is going to be 7,384 divided by 3,600. Go ahead and see how many times 3,600 fits in there. 7,384 divided by 3,600 using the division sign on your calculator. It goes in twice. Ignore the decimal, just take the whole number. 2 times 3,600 is 7,200. Subtract 184. Okay, so here's what's going to happen. The 2 is going to go in my 3,600 spot. But then with the 184, I now need to see how many sets of 60 is in that thing. So that means I'm going to take this remainder and go divide it by the next thing. I'm going to take that 184 and divide by the 60 because I need to know how many sets of 60 are in there. We actually did this earlier. We actually divided 184 by 60 earlier. Go ahead and divide 184 by 60 on your calculator. It will be 3 point something. 3 times 60 is 180. 4. After you divide by 60, the remainder will always go in the ones place. Okay, so we're about to put that number in the ones place. We're about to put that number in the 60s place and that number in the 3600s place. Okay, so watch how this is going to work. We're going to have 2 sets of 3600, big space, 3 sets of 60, another big space, 4 sets of 1. That is going to be my answer. 2 sets of that. This is the 3600 space. 3 sets of that. That's the 60s place. And then after you divide by 60, that always goes in the ones place. The final remainder always goes in the ones place. So that's my answer. The spaces are super important. If you didn't put those spaces and you put them all next to each other, it would just equal to 9. You got nine of those things. But the spaces are a big deal. Putting those spaces there makes it equal to 7,384. So again, we're saying we have 2 sets of 3,600. We're saying we have 3 sets of 60. And we're saying we have 4 sets of 1. And if you go through all that math, it will be equal to that. Got to do long division. We got two more examples left. This is a very good time for these last two examples to pause the video and see how you do. See if you can get these correct. These are not easy. These are big, ugly answers. Neither one of them are as big. They're pretty big, right? Neither one of those two are as big as that, though. We're not going to need to divide anything by 216,000. That's not as big as 216,000, and that's not as big as 216,000. So I'm not going to need to go into the 216,000s place. I'm probably going to start each problem by dividing by 3,600. And then after you divide by 3,600, take that remainder and divide it by 60. You're probably going to need two long divisions on each of these. So pause the video, try it, come back, see how you did. I'm going to go ahead and tell you the answer. It's actually kind of, especially this one's pretty long. So this is going to be 19. I need to leave, make sure I give myself enough room. 19, so 10, and then 9 of these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 19, and then big space, then 33. There's 30, there's 3, big space, and then 11, and then 1. This is the final answer for 70,391. How would that have come up? I mean, how would we get that? Remember, you don't have to do it the way I'm doing it right here. I just like to do it this way. I like to write down my powers of 60 like this. And then once I hit an answer that's bigger than the number I'm dealing with, so 216,000 is bigger than the number I'm dealing with, I say, okay, I'm not going to need that one. I don't need to divide by 216,000, but I do need to divide by 3,600. So that's what I'm going to do. Like, that's how I would do the problem. That doesn't mean you have to do it that way if you can come up with your own way. But, you know, when the wife and I are sitting at home on a lazy Sunday afternoon by the fire, converting Hindu Arabic numbers into Babylonian numbers, this is just how we like to do it. So we're going to start by taking 70,391 divided by 3,600. Go ahead and get your calculator. 7,391 divided by 3,600. It goes in 19 point something times, right? And ignore the decimal, take the 19. That's where this comes from, the 19. Go 19 times 3,600, you get 68,400. And subtract. Should get 1,991. That's the number that you're going to take and divide by 60 now. Go ahead and take 1,991, divide by 60, you should get 33. That's where that 33 comes from, 33 point something, but just take the whole number part. Now multiply 33 times 60, you should get 1980. Subtract those numbers, you should get 11. That's where that comes from. 19 goes here, 33 went there, 11 went there. We're done, right? That's the math you would go through to get that, okay? That means 70,391 is equal to 19 sets of 3,600 plus 33 sets of 60 plus an extra 11 at the end. It's equal to 19 sets of 3,600 plus 33 sets of 60 plus 11 sets of 1. And for this final one, I'm going to go ahead. Let's actually work through this one. Um, Very similar. I don't need to draw this again because this number is not that big, right? 147,000, it's big, but it's not 216,000 big. So I don't need to divide by 216,000. The only time I would need to divide by 216,000 is if I was starting with a number that's bigger than that. So I'm going to divide that by 3,600. And then I'm going to take my remainder and divide by 60. There's going to be two long divisions going on here. So I'm going to take 147,605 and divide by 3,600. Exactly like we did up top. 147,605 divided by 3,600 is 41 point something. Just take the 41, ignore the decimal. Go 41 times 3,600, that's 147,600. Subtract, we get 5. What did I do with my remainder here? I divided that by 60 because that's the next place value moving over to the right. So what am I supposed to do? I'm supposed to divide that by 60. I know that's weird and that looks very strange, and some people freak out here. They're like, I must be doing something wrong because 60 doesn't go into 5, right? Some people might just say, well, that doesn't look good. I'm going to trade it around. But no, we're not doing 60 divided by 5. We're doing 5 divided by 60. I'm trying to see how many sets of 60 go into 5, which it doesn't, right? Of course, if you take 5 divided by 60, you're going to get 0 point something. 0 times 60 is 0. We get a 5 right there. It just means I'm going to have a 0 in my. Remember, the Babylonians have a symbol for 0. 0 is okay. Like, pretty much everything we've done today is ones and tens, but sometimes 0 shows up. Those two triangles represent 0, remember? And so it simply means I have 41 sets of 3,600. 2, 3, 4, 41. And then I have 0 sets of 60. That just means we put the double triangle. That means 0. And then I have 5 sets of 1 at the end. 2, 3, 5. The final answer is this right here. I know that's weird, and people don't like the 0 thing, but we divided by 3,600, we got 41. There's the 41. Actually, I only wrote 31, didn't I? Let me squeeze an extra 10 there somewhere. Let's squeeze an extra 10 right there. Okay, now we're good. There's 41. 2, 3, 4, 1. Okay, so we got 41. And then we have 41 sets of 3,600. We have 0 sets of 60. And we have 5 ones left over there at the end. It's exactly the same thing we did up here. It just was weird because we got 0 there, right? That's because 5 is too small. 60 didn't fit into 5. It just happens to have a 0. Sometimes you get zeros in your number. Sometimes we get zeros in our number. We got zeros all over the place up here. But sometimes the Babylonians had zeros in their number. Okay. This is 41 times 3,600 plus 0 times 60 plus 5 times 1. Okay. That is it for this section. Thank you for watching.